All right, good morning. It's a pleasure to be here today. My presentation will be in two pieces. I'll shake things up a little bit. I'll have a video, but the first part I'll do a bit of context for AGA. I'll have 3 or 4 slides, and then I'll show a video on the technology. And I think in some ways, Bristow set it up very nicely because one of the key features of the technology is to reverse this declining mineable gold grade. So I'll go over that. So I'll just start off with the presentation. So this first slide, I'm not going to obviously read this to you. It's got important forward-looking statements in it, so I would encourage people to read it. The AngloGold Ashanti global footprint is quite significant. You know, we're virtually mining on numerous continents across the world. We have a balanced portfolio across continental Africa, South Africa, the Americas, and Australia. And our 3 major growth projects are centered around continental Africa, the Americas, and Australia to help balance up that portfolio. And as you can see in the bottom right corner, you know, we have a very strong balance sheet, strong EBITDA, and all the way through to a low net debt. So the company's in extremely good financial shape from that point of view. When you look at what's happened from 2008 through to 2011, you can see across the global portfolio there's been a substantial increase in the EBITDA in all of the major regions, going from around $1 billion in 2008 up to $3 billion at the end of 2011. Now, of course, as was alluded to, that there's this, you know, with Mark Cutifani moving on, there is a global search underway, and the board is taking that process forward, and we're looking at a number of internal and external candidates. But in the interim, there are 2 people who have stepped up. One is Venkat, the CFO, and Tony O'Neill. And Venkat will look after the finances and the corporate functions, and Tony will look after the operations and exploration. Both are extremely experienced. Both are very knowledgeable with AGA, and there'll be, you know, really little change in the direction of the company. And to support that, there is a very deep bench of executive and senior managers throughout the operation. And the strategic direction that was defined in November remains unchanged, and you can see the points highlighted there. Now, when I came out to AngloGold Ashanti in South Africa in late 2010, and it was to look at what can be done about unlocking the 100 million ounces that were here in South Africa. We had a traditional mining flow sheet, and there was thought to be, as we go to 5 kilometers, because that's where the reserves are, that was going to be, there was some significant challenges. And so initially what we looked at, we saw declining grades, declining production, and rising costs. And when we looked a little deeper and said, okay, well, what's driving that? What we found was 3 key things. One is we were leaving about 40% of the reserve behind for stability pillars as part of the mining method. When we looked at our ore bodies, most of them were sort of in this range. They were, you know, 20, 30, 40, 50 centimeters. And what was happening was, because of the mining method, we were opening up the openings to put people in and equipment, and we were experiencing dilution plus 200% depending on exactly the mine. And finally, when you looked at the complexity to get down to, currently down to 3.5 kilometers, you take 3 shafts, the effective working time on a face was under 30%. So it was really, that was the problem that we needed to be solving. And so what I'm going to show you today is our thinking on what is the technology that will actually solve that problem. So what I've got now is a video, and I'll just run you through that. Okay, there's a short intro here with a video, with an audio part, so I'll just let it play for about 30 seconds.
Headquartered in Johannesburg, South Africa, AngloGold Ashanti is the 3rd largest gold producer in the world. The company has operations on 4 continents, as well as several exploration programs in both established and new gold-producing regions. In South Africa, AngloGold Ashanti currently operates 6 deep-level underground mines as well as a surface operation in their West Wits and Vaal River operations.
Okay, can you stop it there, please? So what we're looking at here is we're looking at one of our mines, and the scale here is about 4 kilometers by 4 kilometers. And when I was looking at it and saying, trying to get a handle and an understanding of what the ore body looked like, you know, it's a relatively flat, shallow dipping deposit, but as you can see, it's broken up into all kinds of pieces. If you just play the video again, please. So what you're looking at is obviously a 3-dimensional view of the ore body, and it's one of the things that's broken up into all of these pieces. If you just stop it there, a little bit further, just another couple seconds. Yeah, right there. And what you can see is it's broken up into all of these individual pieces. And these pieces are actually quite substantial. So on a macro view, it's very disrupted. But when you actually now, when we'll play the video a little longer here now, we'll start again. When you actually go in on a much smaller micro scale, what you'll see, if you just play the video again, what you'll see when you go in on a smaller scale and we look at one of these individual pieces, they're actually, if you just stop it there probably, what we're seeing is that these pieces are actually large enough to do an individual mine design on. They're sort of in the range of 50, 60 meters in this dimension. And if you just play the video there a sec, yeah, right there, that's good. And along strike, you know, they're probably 100, 150 meters. That's plenty large enough to actually go in and do individual mine designs on. And then the second question was, okay, on a macro scale, you seem to have solved the complexity of the ore body looking at a new mining flow sheet. And then the issue is on a micro scale, which is this, what's the level of disruption of the ore body? So there is minor folding and faulting, but it's actually very minor. So what we're thinking about, as you can see, is coming in on something like 30-meter sublevel spacing and actually bore the reef out in between in a continuous method. And so this, when your reef is sort of 10 or 15 or 20 centimeters, you can actually take out all of the gold. So the catchphrase that we looked at when we started this project is to say that the solution to what we're trying to accomplish here is we want to mine all of the gold, we want to mine only the gold, and we want to mine all the time. Okay, so if you just continue with the video. Okay, if you just stop it there for a sec. One of the things that characterize the South African ore bodies as part of AngloGold Ashanti is that we would have maybe 20 or 30 or 40 diamond drill holes, where what I'm accustomed to would be thousands. And in terms of switching from what I just showed you, we're going to need significantly more information. We're going to need thousands of holes to actually identify every one of these individual small terraces where we're going to build a mine design on. And so what we've come up with is an approach to do ore body information that isn't diamond drilling, that will effectively be able to drill at 10 times the rate at a tenth the cost. So that was part of the project to crack that equation. So we just continue, and I'll show you what our thinking is here on essentially this is ore body information. So this is an animation about the drilling that we're proposing. If you just stop it there for a sec. What you can see is we're going to come in underneath the ore body, and we're going to drill in a very traditional way. We're going to be drilling diamond drill holes up to identify those individual reef planes so that we can build a mine design on them separately. Okay, if you just continue. The other thing that's a feature of this project that we've undertaken is every single piece of technology is existing. So what we said is we don't do prototypes. If you just stop it there for a sec. If you don't, we don't do prototypes, and we don't do ideas, and we don't do concepts. It has to be existing technology that we pull together in new and creative ways. So that's what you're seeing here. Everything you see is existing technology, and what is sort of the innovation side of it is how we've decided to put it together. So if we just continue with the video. So what you're seeing is just, it's a drill, it's from Cubex, it's standard technology around the world, and this is off the shelf, proven technology. So you just stop it there for a sec. This was a really kind of a breakthrough project for us. So what I showed you was up here, that's the drill. What we're doing for ore body information is we say, okay, we drill the hole, and then what we do is we put a gyro up in the hole to get the three-dimensional location. What we then do is we put a surveillance camera up in the hole that has the technology to take a 360-degree image, and it's got software to flatten that out and build up the resolution. And the first time we tried this technology, there's the resolution that we got. And the resolution was more than what was required to identify, are you in reef, are you in footwall, or are you in hanging wall? And so what this allows us to do, when you look around the world, probably 90% of the holes that are drilled in ore bodies overseas are for ore body configuration, ore body location, ore body shape, and maybe 10% is for ore grade, but we continue to do it in the most expensive way. So what this is doing is going to completely change the way ore body information is thought about and acquired, I expect, likely around the world. And the final feature here is what we've done is we've formed a global technology consortium to help us. Essentially, our research arm was an external group called the Global Technology Consortium, and there's the team. It was Sandvik, Cubics, and Connors who have put this project together for us. And essentially, this one is, like I say, I expect this one to end up overseas. It's not going to just be for the deep South African mines. Okay, if you just continue the video. The next piece here is tunnel boring, and I'm sure most people have some sort of a relationship to tunnel bores. They're essentially a construction tool for doing tunnels in the Alps and such, and they don't really have a place in the mining industry, and they're rarely being used. If we just stop it there. And the reason they're not used in the mining industry is first off, they don't fit in a mine. They're hundreds of meters long. And the other thing is they're not very flexible, where the current mine designs require a lot of development or a small amount of development in a lot of locations, and a tunnel bore will bring you a lot of development in one or two locations. But the first thing that we've been looking at is to say that this long train that sits behind the tunnel bore is typically a couple hundred meters long, and what we've done is we've looked at every module, and essentially every module can be taken off that, and it can be serviced in a different way, which leaves you with a machine that's fundamentally about 17 meters long. But the thing is, it's not reversible in its current configuration. So we're working with a tunnel boring company out of Germany to actually make the head detachable, and then to make this is a walking mechanism that allows it to walk forward, and to redesign that walking mechanism to walk backwards. And then what we'll do is we'll flange this main beam when it's moving backwards. So you're going to end up with a machine that's probably 15 meters long that can obviously excavate a tunnel going forward, but actually can walk backwards at probably about a meter an hour or a meter a minute, and end up in another heading. The thing about a tunnel boring is that it absolutely completely changes the single-headed development advance rate from 3 meters a day to something like 10 to 20 meters a day. It will make a step change in the mining intensity. Okay, continue, please. So what we're showing now is essentially how this sort of fits into the overall mine design. They're sort of showing you the reef plane. I think it'll pan out here in a second. Okay, if you just stop it there. So now what our thinking is obviously it's reef boring. So we're just going to take existing technology, small drills, small raise bores, and we're going to ream up. And if the ore body is 20 centimeters, we'll take 20 centimeters out. If it's 50 centimeters, we'll take 50 centimeters. If it's a meter, we'll take a meter. When I came over to South Africa, my relationship with gold mining was you're a gold mine when you're, 4 or 5 grams a ton. The head grade, I was told in South Africa when I came out here, was 7. So I'm saying, okay, that's good. When you get in underneath the hood, and if you could take the dilution away, these ore bodies that we have, and we have 100 million, in the range of 100 million tons of resource, these ore bodies, many of them are over 25 grams a ton. These are real gold mines, seriously gold mines. And so the trick is that if we can replace the dilution, remove the dilution and replace it with reef, not only would you would you see a flattening of the gold grade. We would expect to see a significant increase in the gold grade in our operations. And the simple equation that I use, we take a mine like Mponeng, a third of what we hoist is rock for access development, a third of it is reef, and a third of it is dilution. And the goal is to remove the dilution and replace it with reef. And so with that very, very high level equation, you know, a mine like Mponeng with 400,000 ounces, if we could get this right, you know, we'd be targeting something like, you know, 600,000 ounces, and you wouldn't need any additional infrastructure, no additional costs. There's, you know, you get it essentially in some cases just for free for the investment and the change in the technology. Okay. So what you're seeing here is just some of our thinking initially about that we would be in the bottom drift. So what you're seeing right here, if you just stop it right there, what we're seeing here is we're showing you the animation, and now what we're showing you is the actual footage from the drilling that we've been doing. So we've been testing the idea of boring the reef out. So if you just continue the video, so that's what you're seeing here is that drift or that drill is breaking through into the upper sublevel. And now this is, if you just stop it there, this is an example of just existing technology off the shelf. And here we're doing a 1 meter hole, but we've tested them down to around half a meter. And there's a number of existing machines out on the market that can do this, and we're busy working with suppliers to get a Mark II and a Mark III and a Mark IV that essentially make the machine smaller, more powerful, and faster. Okay, you just continue. So again, this is all just existing technology out in the industry. We haven't invented anything. It's not a prototype. So if you just stop it there for a sec. What you're seeing here is you're seeing one of the holes that we drilled. It's hard to see, but the reef is sort of right here. And the issues that we were dealing with when we thought about this, people said, you won't be able to keep the hole straight. The hole will drop. You won't be able to complete the hole. If you do complete the hole, we're in a shaft pillar at 10,000 feet. Probably stressed equivalent to 15,000 feet, that you won't be able to keep the hole open. There'll be rock bursting. There'll be all kinds of problems. And there's a photo just to show you that all of those problems that we were concerned about, none of them materialized in this particular hole that we did. So I guess what I'm trying to do is I'm trying to leave people with the idea that you know, there's lots of challenges with this project, but we've overcome a lot of them as well. Okay, if you continue. So again, this is just, you know, seeing it, the whole operation. It's a continuous operation. So in terms of us meeting the test of all of the gold all of the time, this would be a continuous operation. There'd be no need to stop this operation. People would essentially change on the job. It would be much like a concentrator or a smelter around the world. So all of the blasting and the shift changing and all of that sort of stuff, what you're seeing here, this animation would remove all of that inefficiencies. So it's more just views of what's in our head in terms of helping people understand what this thing might look like. The other one, you might stop it right there, yeah. The other one is we're working with high strength backfill. In terms of trying to get all of the gold, right now we're leave stability pillars, and what we're saying is if we want to take all the gold, we need to be putting back something that's similar in strength to what we take out. So we've designed that project, and I'll show you just now here some of the trials that we've done. But essentially, if you think about underground mine backfill, it's 2 or 3 MPa. Low strength concrete is 20. High strength concrete is 60. What we have already, we're up to 170 MPa. So that's really what we're trying to put back is a high strength backfill so that we can essentially remove all of the gold and not have to leave stability pillars. Okay, if you continue. This is just more of the same, I guess, the same views that you've already seen. Now, one of the things that when we've looked at this this project, you could see it in 3 different lenses. I would offer you to look through this project through 3 different lenses. One, the first lens, if you just stop it there, this is sort of the backfill, so I'll just let it continue, but this is the backfill trials, just to show you what we've been testing. This is back about 3 or 4 months ago, and so we've advanced this, and we're now have a 1,000-meter loop, an incline by about 20 meters, and we're pumping the material around, dealing with the pumping issues. Okay, if you continue. Yeah, I would invite you to look through this through 3 lenses, and one is that we're dealing with and unlocking the 100 million ounces in South Africa. The second issue is that, we could be, developing technology that is unique for the deep underground mining in South Africa. If you just stop it there for a second. And that second lens is, we could be turning the obvious, what appears to be a sunset industry in South Africa in the deep gold, to possibly a sunrise. And the final one is that we believe really is that if we get this right, and we have the patience and the persistence to continue with this, is that we'll actually change the mining paradigm for deep underground hard rock mines worldwide. So what you're seeing here is a view on the mining intensity. This was how we took a large block, did a back calculation from 1.6 kilometer to 1 kilometer block of ground. It took roughly 15 years to mine out with the traditional method. With what I've shown you here, it's sort of, we're mining it out in a fifth the time. That's the mining intensity that you get, because if you remove the dilution and can't increase the intensity, you won't be able to fill the shaft up with reefs. So this clearly shows that we believe we've cracked the mining intensity issue. Okay, if you just continue that. And you can just stop it there. And the very odd thing, about this is that this project in the 70s was done, and they ran into a major problem on backfill, and essentially declared the project a failure because they didn't have backfill. Now, I know it's hard to believe today that a project could fail on backfill, but if you read through that this was essentially done in 1974, and all of the goals around all the gold, only the gold all the time, was essentially articulated, it was invested in, it was, in our opinion, pretty much solved, and all we're doing is just replaying that tape, and this time we're going to be more persistent and make sure that we make this happen. And I think that concludes the presentation.